Scientists have discovered exoplanets where gravity far exceeds Earth's, creating conditions that dramatically affect life, atmosphere, and geological structures in ways that seem almost impossible to imagine. Gravity, a fundamental force, depends on a planet's mass and radius, meaning even small differences in size can result in extreme weight variations for objects and organisms. High-gravity planets are rare, yet advances in telescopes and orbital observations have revealed candidates with gravity multiple times stronger than our own Earth. Such high gravity influences a planet's surface, causing denser atmospheres, more compact mountains, and flattened landscapes due to immense downward force over millions of years. Any human or Earth-based life would struggle, as muscles, bones, and cardiovascular systems are not adapted to withstand such relentless pressure from the planet's mass. Scientists speculate that high gravity affects liquid and gas behavior, altering ocean tides, cloud formation, and atmospheric circulation in ways that challenge Earth-based physics. On these planets, even light materials fall faster, and projectiles experience increased resistance, making movement and simple tasks extraordinarily difficult for any hypothetical visitor. Researchers use mathematical models to predict conditions, simulating weight, pressure, and environmental effects to understand how life, if possible, could adapt to such extreme forces. Studying high-gravity planets expands understanding of planetary formation, helping scientists refine theories about how mass distribution and density affect celestial evolution. Space agencies analyze light spectra and orbital patterns to infer surface conditions, estimating gravity based on planet size, density, and its effect on nearby celestial bodies. High gravity reshapes planetary geology, compressing crusts, influencing volcanic activity, and creating immense tectonic stress over millions of years. These planets often have high core density, contributing to intense gravitational pull and influencing magnetic fields, which in turn affect atmospheric retention and radiation shielding. Observations suggest that high-gravity planets may have stronger atmospheric pressure, making flight, weather, and cloud dynamics radically different from Earth. Life forms, if present, would need extraordinary adaptations, such as strong exoskeletons, compact bodies, and reinforced cardiovascular systems to survive high-pressure environments. Scientists theorize that evolutionary processes would favor shorter, sturdier organisms with enhanced muscle density and skeletal strength under high-gravity conditions. Even plant-like organisms would require structural reinforcement, potentially producing thicker stems, compact roots, and low-to-the-ground growth patterns to withstand gravitational stress. High gravity influences erosion, sedimentation, and rock formation, creating landscapes that appear alien, with flattened mountains, dense plains, and compressed canyons. The planet's rotation may slow under gravitational constraints, affecting day length, wind patterns, and atmospheric dynamics in unpredictable ways. Astrophysicists study these worlds to test the limits of known physics, exploring how high gravity interacts with energy, motion, and planetary stability. Any human mission to such a planet would require advanced exoskeleton suits, reinforced habitats, and careful planning to counteract the overwhelming gravitational force. High gravity also impacts water distribution, making oceans denser, tidal forces stronger, and weather systems more violent and unpredictable. Theoretical models suggest that high gravity could compress gases, thickening atmospheres, and altering chemical reactions critical for supporting life. These conditions challenge our understanding of habitability, as high-gravity planets may host entirely unfamiliar ecosystems, if life exists at all. Studying them informs not only planetary science, but also engineering, biomechanics, and materials science, inspiring innovative solutions for high-pressure environments. Gravity affects orbital mechanics, meaning satellites and moons around such planets must maintain precise velocities to avoid crashing due to excessive pull. High gravity may influence star-planet interactions, potentially causing tidal locking or unusual orbital eccentricities observable from Earth. Understanding such worlds helps refine criteria for habitable zones, revealing how gravity, atmosphere, and stellar proximity intersect to permit life. Astronomers rely on gravitational lensing, spectral analysis, and stellar motion to estimate planetary mass and infer high gravity conditions indirectly. Exoplanets like this challenge imagination, as no human has experienced such intense weight, prompting speculative designs for exploration equipment and adaptive technologies. Imagine arriving on a world where gravity presses everything downward with incredible force, shaping landscapes, oceans, and even the smallest forms of life in completely unfamiliar ways. On a planet with extreme gravity, the surface would feel intensely heavy, and every step would require far more effort than the simple movements humans experience on Earth. Scientists believe such gravity would reshape the entire environment, influencing how mountains form, how rivers flow, and how the atmosphere behaves across the planet. Mountains might appear shorter than those on Earth because intense gravitational pressure would prevent rocks from rising too high before collapsing under their own enormous weight. Rivers could flow slowly and steadily as the force of gravity pushes water downward while also compressing landscapes into flatter, denser terrain. Oceans might be deeper and heavier, with water layers compressed together more tightly due to the planet's strong gravitational pull. The atmosphere would likely become thicker near the surface because gravity would pull gases downward and keep them concentrated close to the planet. This dense atmosphere could create high-pressure conditions similar to deep ocean environments on Earth, affecting temperature, wind patterns, and weather systems. Strong gravity might reduce the height of clouds, forming low and dense cloud layers that drift slowly across the sky. Weather systems on such a world could behave very differently from Earth, producing powerful winds, but within a compressed atmospheric space. Rainfall might fall faster and strike the surface with greater force, shaped by the planet's stronger gravitational acceleration. Lightning storms could appear more intense due to dense atmospheric layers storing and releasing electrical energy. Even sound might travel differently because compressed air changes how vibrations move through the atmosphere. Under these conditions, any life forms evolving on this planet would need remarkable adaptations to survive the constant pressure of gravity. Scientists imagine that creatures might develop strong, compact bodies designed to support their weight in the intense gravitational environment. Instead of tall animals like giraffes, life forms might remain close to the ground, with thick limbs and reinforced skeletal structures. Shorter and broader body shapes would help distribute weight more evenly, reducing strain caused by the planet's powerful gravity. Muscles might be extremely dense, allowing organisms to move efficiently despite the heavy force pulling them downward. Hearts and circulatory systems would likely evolve to pump blood effectively through bodies experiencing higher pressure conditions. Bones could be thicker and stronger than those on Earth, providing support against the continuous pull of gravity. Even small movements would require energy, meaning creatures might evolve efficient ways to conserve strength. Some species might move slowly but powerfully, conserving energy while adapting perfectly to the heavy environment. Plant life would also look very different compared to the tall forests commonly seen on Earth. Trees might grow shorter and wider, with thick trunks capable of supporting their weight under the planet's intense gravity. Instead of tall branches stretching upward, plants might spread outward close to the ground for stability. Leaves could be smaller and stronger to avoid tearing or collapsing under gravitational pressure. Root systems would likely be deep and dense, anchoring plants securely within the compressed soil. Soil itself might be compact and tightly packed because strong gravity continuously presses particles together. This could make plant growth slower but also more stable in the long term. Ecosystems would evolve gradually, shaped by environmental pressures, unique to such a powerful gravitational field. Scientists studying these possibilities rely on advanced computer simulations and planetary models. These simulations help researchers understand how gravity influences climate, ecosystems, and geological processes over millions of years. Understanding such environments helps scientists expand their ideas about what conditions might support life beyond Earth. Some researchers believe that extreme gravity does not necessarily prevent life, but simply encourages different evolutionary solutions. In fact, diversity in planetary environments could lead to unexpected biological creativity across the universe. Studying extreme gravity also improves our understanding of physics and planetary formation. Massive planets often form from dense materials and powerful gravitational forces during early solar system development. Observations of distant star systems reveal many planets far heavier than Earth. These discoveries challenge previous assumptions about how common Earth-like conditions might actually be. Some exoplanets, discovered by astronomers marins, imagine astronauts preparing to visit a distant planet where gravity is several times stronger than Earth's, requiring technology, training, and creativity far beyond ordinary space missions. Before attempting such a journey, scientists must carefully calculate the planet's mass, surface gravity, atmospheric pressure, and environmental conditions. These calculations ensure exploration missions remain safe and scientifically productive. Space agencies rely on robotic probes and orbiting spacecraft first, gathering data about the planet's gravity field, atmosphere, and surface. These robotic explorers provide crucial information before humans ever attempt landing. Robotic data helps engineers design equipment capable of functioning where gravity could place tremendous strain on machines and materials. Landing on a high-gravity planet would require spacecraft with extremely powerful engines capable of slowing descent against intense pull. Even after landing, spacecraft structures would need reinforcement to prevent damage from constant gravitational pressure. Astronauts would likely train for months or years in simulated environments designed to replicate heavy conditions. Specialized training facilities might use centrifuges or weighted environments to prepare explorers for extreme gravitational pressure. Walking on such a planet would feel drastically different from walking on Earth, as every step would require far greater effort. Even lifting small tools could feel exhausting because the weight of objects increases dramatically. To overcome these challenges, astronauts might wear powered exoskeleton suits that assist movement and reduce physical strain. These advanced suits could contain motors and support structures that help astronauts stand, walk, and carry equipment. The suits would also need strong materials to handle atmospheric pressure and gravitational stress without failure. Oxygen supply systems would remain essential, especially if the planet's atmosphere contains gases unsuitable for human breathing. Communication systems would connect astronauts with orbiting spacecraft and mission control on Earth for constant monitoring. Even simple scientific tasks could become difficult because instruments must operate correctly despite increased gravitational pressure. Cameras, sensors, and sample collectors would require reinforced components to function reliably in demanding conditions. Robotic assistants could perform tasks that might be physically difficult or dangerous for human explorers. Small robotic vehicles might travel across the surface, collecting geological samples and mapping terrain efficiently. Drones designed for flight might struggle in strong gravity, but dense atmospheres could sometimes provide enough lift for specialized aerial vehicles. Scientists would study rocks, soil, and atmospheric composition to understand how the planet formed and evolved. Geological samples could reveal information about the planet's internal structure and history of volcanic or tectonic activity. Extreme gravity might compress rock layers, creating unusual geological formations rarely seen on Earth. Studying these formations would help scientists better understand planetary physics and how gravity shapes landscapes. Researchers would also measure atmospheric pressure and temperature to understand climate patterns on the heavy planet. Weather systems could behave very differently due to the influence of stronger gravitational forces. Wind movement, cloud formation, and rainfall patterns might follow unfamiliar cycles shaped by the planet's dense atmosphere. Astronomers and planetary scientists would analyze these systems carefully to expand knowledge of planetary climate diversity. Exploration missions might also search for signs of past or present microbial life. Even simple forms of life would be an extraordinary discovery, showing living systems can adapt to extreme conditions. Scientists would examine soil chemistry, water presence, and environmental stability to determine whether life could exist. Laboratory experiments on Earth often simulate high-pressure conditions to study how organisms might adapt. These studies suggest life could evolve unique biological structures to survive intense gravitational forces. Discovering such organisms would reshape scientific understanding of life's adaptability across the cosmos. Human exploration missions would likely remain short due to the intense physical strain caused by high gravity. Astronauts might work in carefully timed shifts to limit exposure and maintain peak performance. Imagine standing on a world where gravity constantly presses downward with tremendous strength, slowly shaping every mountain, valley, ocean, and atmosphere over millions of years. On such a planet, the landscape would evolve very differently from Earth because gravity influences how rocks move, mountains rise, and rivers carve their paths. Scientists believe that extreme gravity prevents mountains from growing very tall because the enormous weight of rock eventually collapses under its own pressure. Instead of towering peaks like those on Earth, the surface might contain wide hills and dense rocky plateaus. Geological structures would appear compressed, almost as if the entire planet had been gently pushed downward by an invisible force. The crust of the planet could also be thicker because intense pressure keeps layers tightly compacted. Volcanic activity might still occur, but eruptions could behave differently due to the strong gravitational pull acting on molten rock. Lava might flow slowly and heavily across the surface before cooling into thick, dense formations. Scientists study volcanic behavior under different gravitational conditions using simulations and laboratory experiments. These studies help researchers understand how gravity influences planetary geology across the universe. Extreme gravity also affects how rivers flow across the planet's surface. Water would move with powerful downward force, carving valleys, but also slowing as friction increases under heavy pressure. River systems might appear shorter but deeper, with steep channels cutting through compressed rock layers. Lakes and oceans would also behave differently in such environments. Strong gravity would pull water tightly toward the surface, creating deeper ocean basins. Waves might appear smaller in height, but heavier in motion due to the weight of water itself. Ocean currents could move more slowly because the dense atmosphere and gravity combine to resist rapid movement. Weather patterns would also change dramatically under these conditions. Dense atmospheres caused by strong gravity could trap heat more efficiently near the planet's surface. This effect might create warmer climates or stronger greenhouse conditions depending on atmospheric composition. Clouds could appear thicker and closer to the ground because gravity pulls atmospheric gases downward. Rainfall might fall faster and strike the ground with stronger impact than rain on Earth. Over long periods, this powerful rainfall could shape valleys and rock formations in unusual ways. Wind systems might also behave differently because dense air resists rapid movement. Storms could still form, but their structure might be more compact and concentrated. Lightning storms might appear intense due to the energy stored in thick atmospheric layers. These storms could illuminate the skies of the planet with dramatic flashes of light. Scientists believe atmospheric pressure on such planets could be several times higher than Earth's pressure. High-pressure environments influence chemical reactions in the atmosphere. These reactions could create unusual clouds, colors in the sky, or even unfamiliar weather patterns. Gravity also affects how the planet rotates over long periods. Heavier planets sometimes rotate more slowly, creating longer days and nights. Longer days could influence temperature changes across the planet's surface. Some regions might experience extended daylight, followed by long periods of darkness. These cycles would shape climate patterns and possibly influence the evolution of life. Another important effect of extreme gravity involves the planet's internal structure. The core of such a planet could be extremely dense, made of heavy elements compressed under intense pressure. This dense core might generate a powerful magnetic field surrounding the planet. Magnetic fields play an important role in protecting atmospheres from harmful cosmic radiation. A strong magnetic field could help the planet retain its atmosphere for billions of years. This stability could allow complex weather systems and geological processes to continue for long periods. Scientists often study these conditions to understand how planets remain stable over time. Understanding gravitational effects also helps researchers improve models of planetary formation. During early solar system development, gravity determines how planets gather mass from surrounding material. Massive planets continue attracting material until reaching their final size and structure. Observing distant planets helps scientists confirm these theories about planetary growth. Each discovery adds valuable information about how diverse planetary systems can be. Some planets may be only slightly heavier than Earth, while others are dramatically more massive. Extreme gravity planets represent one of the most fascinating examples of this diversity. These worlds demonstrate how different planetary environments can be from Earth. Imagine a future where powerful telescopes reveal hundreds of distant planets with gravity far stronger than Earth's. Astronomers continue scanning the skies, discovering new exoplanets whose enormous mass creates gravitational forces far beyond anything experienced in our solar system. Each new discovery helps scientists refine theories about how planets form, evolve, and interact with the stars they orbit. Extreme gravity planets are particularly valuable for research because they reveal how physical laws operate under powerful conditions. Studying these worlds allows scientists to test models of gravity, atmospheric behavior, and planetary structure with greater accuracy. Observatories on Earth and in space work together to detect subtle changes in starlight that reveal the presence of distant planets. These tiny signals help astronomers calculate a planet's size, mass, and potential gravitational strength. As technology improves, future telescopes will detect even smaller and more distant worlds. Some of those discoveries may include planets with gravity many times stronger than Earth's gravity. Such planets challenge scientists to rethink what environments are possible in the universe. They also inspire new questions about how life might adapt to very different planetary conditions. On Earth, life evolved under relatively moderate gravity compared with many possible worlds. But across the galaxy, evolution may have followed completely different paths. Creatures on high-gravity planets might be compact, powerful, and incredibly resilient. Their bodies could be perfectly designed to withstand intense gravitational pressure. Imagining such life forms helps scientists explore the boundaries of biology and evolution. Researchers already study how gravity affects cells, bones, and muscles through experiments on Earth and in space. These experiments help scientists understand how organisms respond to both low and high gravitational forces. Knowledge gained from these studies improves preparation for future planetary exploration missions. Robotic spacecraft will likely lead the exploration of extreme gravity planets in the coming decades. Advanced probes may orbit these worlds, collecting detailed data about their atmosphere and surface conditions. Some spacecraft might even deploy small landers designed specifically for heavy gravity environments. These landers would be built using reinforced materials capable of operating under intense gravitational pressure. Their instruments could analyze rocks, soil and atmospheric chemistry directly on the surface. Information collected from such missions would reveal how these planets formed and evolved. Scientists could learn whether these worlds experienced volcanic activity, shifting crusts, or ancient oceans. Studying their atmospheres could also reveal clues about weather systems and chemical processes. Over time, this research would help scientists classify new categories of planets across the universe. Extreme gravity planets might represent an entirely different class of planetary environments. Understanding them improves humanity's broader knowledge of cosmic diversity. The universe contains billions of galaxies, each with countless stars and planets. Among those planets may exist environments far stranger than anything humanity has yet imagined. Some planets may have crushing gravity, while others may have almost none at all. Each type of planet teaches scientists something new about the laws governing the universe. Gravity, though invisible, remains one of the most powerful forces shaping cosmic structures. It governs the motion of galaxies, stars, planets, and even the paths of light itself. By studying extreme gravity worlds, scientists gain deeper insight into how this force operates everywhere. These discoveries also inspire improvements in physics, engineering, and space exploration technology. Future spacecraft designs may become stronger, more efficient, and better suited for exploring harsh environments. Human curiosity continues pushing the boundaries of knowledge further into the universe. What once seemed impossible gradually becomes achievable through scientific discovery. Generations of astronomers and engineers contribute to the growing exploration of distant worlds. Every observation, experiment, and mission adds another piece to the cosmic puzzle. Extreme gravity planets represent only one fascinating part of this enormous puzzle. Yet they remind humanity that Earth occupies only a small corner of a vast universe. Across that universe exist countless worlds with conditions unlike anything found here. Some may be hotter, colder, heavier, or stranger than any planet in our solar system. Discovering and understanding those worlds remains one of the greatest adventures in science. Powerful observatories and space missions will continue to push these discoveries forward.